Thank you very much. Thank you very much for having me here. I would like to share our experience we gathered in the last year on the use of tensor trains in the optimal control theory. And I will share the results of a series of papers we wrote together with my supervisor, Reinhard Schneider, and another PhD student. And in the end, I would like to present some very new results we did in the last week with Luca Saluzzi and Tizian Wenzel, that is comparing the application of tensor trains with other methods for high-dimensional approximations like kernel methods and neural networks. So our focus was to find quasi-optimal feedback laws for the control of PDEs. And I would try to give a very light introduction in control theory for people who are not really familiar with this. The key objective or the key function that you want to approximate in this whole business of optimal control is the so-called value function, which will allow you to actually calculate the optimal controls for the PDEs. And we would like to use some data-driven methods where data is a very vague word here in this context in order to find this value function. And the ingredients that I will present you step by step are the way how to gather the data, which is either via the Bellman principle or the Hamilton-Jacobi-Bellman equation or the so-called Pontryagin maximum principle. And then how we use this data to approximate the value function by using Monte-Carlo integration methods in a least squares setting. And lastly, I will talk shortly about how we use the tensor trains in this setting. So, this being said, I will give you a very light introduction now to this optimal control setting. So the key idea of optimal control is to steer a dynamical process into a desired end state while exerting as few as possible control, whatever this means. So this is something you need to make precise, and it's different from application to application. I have here some cost function that is one of the prototypical examples of a cost function in the PDE-controlled community. And this would lead us to steer a state into the zero or into the origin of your, in your space. And you have a quadratic cost on the control that you exert while doing this. And the state is restricted to follow some dynamical system that is described by a ODE in most cases, or PDE. And this has a very, very particular form for our setting because this will make the calculations easier, but is also general enough to be of interest in the optimal control community. Yes?
So F and G are what kind of?
They are vector fields, so they're a function from Rn to Rn.
And what, are they differentiable? Are they arbitrary?
So this F and G are given. They are coming from the application that you want. In our case, they are polynomial.
Okay.
So they are very nice functions. But in general, optimal control theory, they should be at least Lipschitz to have a good notion of solution to the ODE. Yeah, but exactly. So in our
polynomials, and so that's correct.
So this is the running example throughout my this work. So this would be a discretization of Schlögel-like PDE, where you have a Laplace-like operator that comes from a finite differences. Oh, I forgot the scaling. And then you have a pointwise nonlinearity in each coordinate, and then you have the controls. And our systems almost always look like this.
Gx is a function from Rn to R, right?
Here, yeah. And the important thing is that the control here is only linearly and here quadratically. And this will make things very easy later for us. But so this is the general control setting we would be interested in later. And we think by now that that our control systems usually come from discretizations of PDEs are one of the reasons why tensor trains might work very well, because you have this very localized structure somehow in the dynamical system. But we could not make that precise yet. But this is somehow the intuition why it's going to work.
So, okay, I'm just trying to understand the context here. So you're trying to minimize, in some sense, x as a function. Should I think of s as time? Is s and t the same?
Yes.
Just different names for the same thing?
Yeah, the s is the time here.
Yeah, okay. So you're trying to minimize x.
Yeah, you start with some distribution or some initial value on your system, and you want to let it goes to 0, to the origin. This is just, so in PDE, let's say you have a temperature distribution, you want that it's 0 everywhere at the end. Right, this is one very particular example of optimal control. But if you have a desired outcome, you can always look then at the difference, and then it will come to more or less the same thing. Yeah.
So I'm just a little confused. U is a scalar function, right?
It depends a lot. I didn't want to make it precise because everything is possible. So if G can be a matrix valued function, and then U can be a vector. In our case, I mean, here it was a vector. Later, we also look at scalar valued U. The thing is, the more control you allow, the easier the system will be. If you have just a scalar valued function, it might be that you cannot even control it to arrive in 0. Yeah. Any more questions right now?
You allow S to go from 0 to infinity or finite interval?
Also, everything is possible. Yeah, so the optimal control problem comes in many flavors. So flavors. You have either an infinite horizon like here, or you have a finite stopping time. You could have ODEs, you could have stochastic differential equation, everything. Everything is possible, and we looked at everything. So, yeah, this is just one example. Yeah. All right. And since we are looking at the discretization of PDEs, the ODEs are usually very high dimensional. And here you need to make a difference between high dimensionality and optimal control and in PDE theory. So in PDE theory, you would go for thousands of degrees of freedom, and optimal control something between 10 and 100. It's already high dimensional there. So we are talking later about 32 and 64. So just to put it in context. If the ODE happens to be linear, so you have a matrix times x plus a matrix times u, and you have this cost function that I just shown you, you can have an explicit representation of the optimal feedback law. So the optimal control that can be explicitly recovered from a matrix that solves the so-called Riccati equation. And this is really the gold standard of in engineering. So this is really what you use. And if your system is not linear, you just linearize it and hope for the best. Then it's still, I mean, it's not optimal anymore, but it works surprisingly good still in these cases. The analogon to the Riccati equation, in some sense, in the nonlinear world, is then the so-called Hamilton-Jacobi-Bellman equation, which is a PDE that describes exactly the solutions of the so-called value function. And kind of complementary approach is the so-called Pontryagin maximum principle that allows you to evaluate this, the optimal costs, so to say, given a certain initial value. And there's a very nice result by Dolgov and all that also looked at the same problem at the same time as us, that have proven that if you are in this linear regime and you have a nice kind of off-diagonal decay of your matrices, then you have nice rank bounds of the TT representation of the value function that I'm interested in later. So in the linear quadratic case, you can actually show that the TT will help you if the system has some kind of locality interaction. So let me introduce this value function. So there is the control, and there is something called feedback law. So the control is just given an initial value of your dynamical system. Then for every time step, I give you the control that steers my dynamics. But alternatively, I can try to find a function that depends on states only, that will give to every state a control. And then if I insert this function into my control, then into the into the dynamical system, then I can recover the optimal control by following the dynamics that I have with this state-dependent feedback. And you can recover the state-dependent feedback from this function that maps basically the initial value x to the optimal costs that I can get given some u in a class by evaluating this gradient. So if this function happens to be differentiable, then I can get an optimal feedback law by this formula, by evaluating the gradient. And an optimal control, the question when this is differentiable is actually not really answered. So you know that it's at least Lipschitz. But it seems that, in certain PDE constraint settings, they have proven that it's infinitely times differentiable. So we think that the setting we are in will fall under this category, but we did not prove it. So the key function we want to focus on is this value function and try to approximate it in some fashion. And so the one way I would like to describe first is this Hamilton-Jacobi-Bellman way. And then later in the talk, I will try to talk also about the Pontryagin maximum principle. So I broke this down very much on a high level, so I don't put the PDE in its entirety. The key observation is that we have a linear operator, differential operator, that takes the function and the gradient and some parameter u, and then you look at the infimum over all u. So actually it looks kind of innocent if you only take this inner part because it's a nice linear operator, but the infimum breaks everything and makes it highly nonlinear and very difficult to handle in the general case. And remember, the value function itself is a function in high dimensions. So this is a very high dimensional PDE, depending on the discretization of the controlled PDE you have. This can be something between 10 and 100. And then the normal methods of PDEs like finite elements or finite difference just fail. And so this PDE is one of these examples where you have this curse of dimensionality. Bellman introduced the term curse of dimensionality for this PDE. And the key observation here is that if I ignore this infimum, I have a nice equation. And then you just say, okay, let's alternate somehow. Solve the nice equation and then change the feedback law with the formula I showed you before, and then solve the nice equation again. And you can replace this nice equation by this integral equation, which is closer to the original Bellman principle that says that every trajectory that is optimal has to have a sub-trajectory that is optimal. And the reason for this, why we looked at this particular reformulation, is that you can make this model free. So you don't really need to know the dynamical system that is underlying this equation.
So
but
are you doing analysis, or are you discretizing and doing stuff?
I want to show you an algorithm on how to approximate this value function.
But the algorithm is based on discrete steps?
The algorithm will be based on some kind of fixed point iteration.
But maybe what's confusing is that at the beginning you get your control, the control problem that you want to solve. That you usually get by discretizing some other people.
Yes, sure.
Right? So there's a two-step thing.
Yeah. So I'm forgetting about the control PDEs. I already used finite differences and talking only about the ODE system that comes from that. And then I have a new PDE that is this HB equation.
And you're going to attack it via discretization, or you're going to attack it via analysis? That's my question.
I will attack the discretization. So the analysis is twofold. So the analysis for the PDE itself is somehow already established, but the numerical analysis of this PDE is very open. But this is, we couldn't do any numerical analysis. I will show you only experimental data in the end. Yeah?
Is L a scalar or?
L?
Yeah.
It's a linear differential operator.
So infimizing it, what does that mean?
The operator evaluated then at axis. So this is, it takes a function v, maps it to a function v, and then you need to infimize over all. I mean, it's a pointwise infimum.
Oh, point five. Okay.
All right. So there's really a big list of literature that try to tackle this HEB equation, and almost all of them somehow fight with the curse of dimensionality. So this has been tackled really a lot from different sides, and in recent years, more and more methods were developed that try to go in higher dimensions beyond 4 or 3. And one of these methods is the so-called policy iteration. And this is exactly what I said, that you try to make an alternating algorithm between solving the linear equation and then updating the policy. So yeah, this is exactly what is written here. And if if the state space in some, I mean, the optimal control setting is really wide. So I presented you now an optimal control setting with continuous space and continuous time. It is also possible in discrete space and discrete time. If you have discrete space, this is actually a Newton-like method, and you can expect a quadratic or superlinear convergence here. And this is why this is interesting for us, because it's in some sense a fast method to evaluate the value of function. However, in the discrete space continuous space setting, the analysis is open. You don't know if it converges, especially if you try to solve this only approximately. However, you have no chance then to solve it approximately, because this is a function equation again. So you need to somehow deal with this. And so this is the key equation that you need to try to tackle somehow. And all methods in the last year that I am aware of, at least, use some kind of Galerkin or least square scheme to solve this equation approximatively. And then use neural networks, sparse polynomials, or tensor trains exactly to solve this linear equation. And this is what we are also going to do. So this was the idea of Reinhold. He wanted to minimize the residual of the equation in the L2 norm, because he thinks that this is easy to do. So, and I mean, if you would get this to 0, then you would exactly solve the equation and everything is nice. And you can use a variety of quadrature rules to solve this integral equation here. And then you need to update your policy, and if your ansatz space that you're using, the model classes, allows for a nice evaluation of the gradient, then this is a very efficient step to take. And tensor trains are very nice for this part, because you can evaluate the gradient very easily. So now the only question is on how to solve this least squares problem here. And the thing that we did is to use Monte-Carlo sampling for the integral. So what is this equation actually saying? So you have some value x. This should denote the transport of this initial value along the trajectory of your dynamical system for time step tau. So you transport just along trajectories for a certain time. And here you gather the cost. This was this x squared plus u squared along this trajectory. And yeah, so you do that for you sample the initial values of your dynamical system, and then you can calculate everything. And then the approximation of the value function, or of the function that is associated with this alpha that you're using at the moment, is just the minimizer of the least squares problem. And this has a very nice model-free aspect to it. That is why we actually started with this. So there's another very famous problem that is related to optimal control, and this is reinforcement learning, that also gathered a lot of interest in the last, like 6 years ago, when AlphaGo really started to take off. And this was the initial point of Reinhold to dive into this direction. So our primary focus was to be model-free. And you can achieve that in this case because you just need a black box how to evaluate a dynamical system at given time instances. So either it's data from some engineers or data from an actual plant or whatever. If you can evaluate at certain times the state and the cost that you have in this time step, then you can solve this, minimization process here. And the tensor trains come into play by saying that the model class later will be exactly this tensor trains. All right. And in the scientific community, computing community, sorry, if you have this kind of minimal residual problem, you usually need to add some extra information because in many cases it's a very unstable, numerical unstable problem. And because of the nature of the optimal control problem, usually, especially if you want to steer to 0, the value function 0 will be 0. And also, usually you have positive costs, so the function is everywhere else positive. And this means that in 0 you have a local minimum. So you want to enforce this two extra conditions. And one way is to put it in the cost that you want to minimize. But actually, a much smarter way would be to put it into the ansatz space. But for tensor trains, especially at the beginning when we started, it was not quite clear on how to get exactly these conditions, because this is picking a certain index set in the tensor trains that correspond to exactly one index in the contracted tensor. This is not easy. And the same also for the gradient. So this is why it ended, in our case, in the cost functional. And also this, in PDE theory in general, if you approximate it somehow, you want to avoid oscillations of your approximant. You don't want the gradient to vary too much. So you introduce an extra regularizing term. In our case, it's the H1 norm, which exactly prevents the gradient from oscillating too much. And again, this can be nicely evaluated in tensor train format if you use the right basis functions in this functional tensor train setting. And actually, this is, using all this information became very popular in the recent years in the neural network community under the name of physical informed neural networks. So physical informed neural networks got really popular in PDE, the solution of PDEs with neural networks. And they also realized that you need to put as much information as possible into your either loss function or ansatz space. So this was the policy iteration. The idea, maybe I should recap it at this point, is that I have an iterative process of solving a least squares problem that is easy to evaluate and then update with the policy with the gradient of the value function, which is also not so difficult. Another approach is to do a direct regression of the value function. So the Pontryagin maximum principle allows me to exactly evaluate the value function at one point and also the gradient if you're interested also in gradient information. However, it's very, very difficult to compute. So this is one of those instances of, let's say, machine learning where the generation of data is very expensive, so you don't want to generate too much data. This is definitely a disadvantage of this method of the direct approximation. And furthermore, the Pontryagin maximum principle gives only necessary condition, so you don't know if you are really find the optimal control. You might be stuck in local minima or something in this direction. And for physically very intricate problems where you need to be very careful with the time discretization, it becomes almost impossible to find the right, to evaluate this Pontryagin maximum principle. On the other hand, this allows us to formulate a very straightforward regression problem. So now we want to just minimize, we evaluate the value function on a given set of samples, and then we evaluate our model class on the same samples, and then we want to minimize the discrete L2 norm. One thing I would like to mention here at this point is also that, so there's a really big difference in using data-driven methods in scientific computing and using data-driven methods in the standard machine learning setting of image recognition or something in this direction. We can generate new samples usually, and we can place the samples very strategically. This is called active learning, and this will play probably a very big role in scientific computing. We did not use it yet, but this is definitely something we want to exploit. And especially some of my colleagues, they are researching on how to do the active sampling correctly for tensor trains, so that you can use as few as samples possible to recover the tensor train that you want. So now I would like to talk a little bit about the ansatz spaces that we used. So when this came up again, the Hamilton-Jacobi-Bellman equation wasn't really tackled for really a couple of decades, actually. And then recently the interest raised a lot. And the first people who tried to go for the Hamilton-Jacobi-Bellman equation again used polynomials. So first they used the full space of polynomials up to a given degree, and then they used sparse polynomials or sparse grids. And then the next step was then tensor trains. And quite parallel to the tensor trains, also deep neural networks came into play in this setting. There's really a vast literature on the use of deep neural networks, and also the so-called kernel methods. And the last, I will try to explain you how we use the tensor trains, and then I will also give a short introduction on kernel methods and neural networks, just to know how what we used in the experiments later. So we use something that we call in our group functional tensor trains. I don't know if this is the same word everywhere. So the idea is that we take some one-dimensional, univariate bases. So in this case, the monomials from 1 to degree k. And then you look at the tensor product of this polynomial basis. So in the end, you just take a look at the products of all possible combinations of basis functions from each variable. And this will give you a basis in the multinomial setting. And then you can expand polynomials by saying that you have some coefficient tensors and the monomials in each variable.
So there's I1 up to ID and I1 up to IN?
Oh, sorry. Yeah, no, this is a typo. This should be an N.
Okay.
This is the... So you take just...
Yeah, so you're looking at all polynomials of degree up to k in n variables.
Yeah, in each variable up to k. So the maximum...
It could be k times n.
Yeah.
There's one.
Yeah.
I see. Okay.
So xi k up to xnk is also part of it. And this makes it quite big, the space.
I got it.
So, and then you have this exponential scaling in the size of the space. And so the way we use now tensor trains is by using, compressing this coefficient tensor. And then we call it a functional tensor train. And that is associated to a certain basis. And I used here monomials because they are nice to write down, but they are numerically really not usable. So you would use something like a Legendre polynomial or Hamid polynomials, depending on how you want to sample later. And then also, just for you, for this notation here, this is the standard notation. I think what we mean here by P is like a map that takes a value, x1, and maps it to the vector that is just taking the basis functions. So this is kind of evaluating the univariate basis on x1, this P. And then if you contract now everything together, you will get exactly a polynomial back. Like in this way. So This is just a way to parameterize polynomials with the help of tensor trains. And this is exactly the way of that Dolgov proved that there's this low rank for the linear case if you have a nice decay of the off-diagonals in the dynamical system. So this is what we mean with tensor train rank in our setting of value functions. And I mean, this is more the slide that we use to promote this in the neural network community. So, I mean, the tensor trains have all these nice properties that they are forming a manifold and that you can actually understand that the geometry and also, at least in some sense, the convergence theory of optimization algorithms. And this is really in stark contrast to neural networks. So this is some kind of advantage of tensor trains in contrast to neural networks. This said, we did not exploit the Riemannian structure yet, but this is still on our to-do list. So we used some ALS-like methods to optimize our least squares problem, but Riemannian gradient descent is definitely something we want to consider at some point too.
So you say it's a smooth object. The collection of tensors that you get is smooth once you fix the ranks?
For a given rank, yeah. If exact rank, right? Not smaller, less.
Oh, I see. Okay. Then.
I mean, if it's smaller, less, it's an algebraic variety. I mean, you have the singularities where the rank drops.
Yeah, that's what I was.
Yeah, no. I mean, but I mean, from a numerical point of view, very likely you will not go too close to the singularities if you're not actively round. But if you actively round, then you can just forget about the higher rank again and then you have a new. I mean, this is a bit the philosophy why we are forgetting about.
So it's, strictly speaking, it's not a manifold, but for your purposes, you're only going to be near this.
I mean, if you fix the rank and do not drop it in some point. I mean,
then it starts getting subtle, right?
Yeah. But yeah, so the manifold for fixed rank, it's.
I got it.
Yeah. Exactly. So the other two methods we'll explain very, very briefly. So one of them are the so-called kernel methods, where you pick a function and two variables, or I mean, two inputs. They can be multidimensional, these inputs. And you usually ask something from this kernel. So usually what is asked is that it's so-called positive definite, and that means that for any choice of points, finite choice of points, you could you get a matrix if you evaluate it at this pairwise points, and this should always be positive definite for every possible choice. This is then a positive summative definite kernel, and one of the real popular examples in kernel in the kernel community is the exponential is the Gaussian kernel. Sorry, they also use the exponential kernel where you don't have the square, and they have really a whole zoo of kernels by now. And one of the very nice properties of these kernels is that the minimizer of this empirical L2 distance has an explicit formulation in terms of the kernels and some coefficients that can be calculated. So so they were very popular also a long time in machine learning as vector support machines. But once, I mean, the kernels itself, I mean, they form a basis again. And the basis depends on the data that you give the kernel. And once you have the data, this is a linear subspace. And this probably is one of the reasons why they don't work so nicely actually in high dimensions. And what we observed in our experiments that they don't generalize at all nicely. So they definitely have some disadvantages, at least how we use them. And lastly, a short word on neural networks. So I think the key property of neural networks is that they have some kind of compositional structure composed of very easy functions. So we are looking at so-called fully connected neural networks. That means that each of the simple function is a linear affine transformation followed by some nonlinear activation. Nonlinear activation means that for each entry of the resulting vector of the affine transformation, I put a nonlinear function. And usually, very popular, the nonlinear function is the so-called Relo rectified linear unit that looks like this. But also there is a whole zoo of activation function that is used by now. And then you need to find the weights and biases, so this W and B. And usually this is done by some kind of gradient-like schemes. So because of this compositional structure, actually, and because of the way you choose the non-differentiability, the nonlinearity, optimizing these neural networks is a very difficult problem in the sense of that actually you can use only gradient-like methods. You can not really use Newton-like methods or other optimization algorithms. And gradient algorithms tend to be very, very slow in high dimensions. So training a neural network takes really a long time until you get something that you are happy with. And then you really don't know where you ended. So it could be a local minima, it could be the global minima, you have really no idea. This is really important because if you then compare the numbers later with our tensor methods, we cannot really say that the neural networks are much worse because we maybe just didn't find the right setting to make them better working. This is a real big problem with neural networks and benchmarking. So the first example I would like to show you some pictures is the so-called control of Rögel-like equations. This is what I started with. So you have a Laplacian and a nonlinearity that acts pointwise. And in this case, we have a scalar control that acts on a sub-interval of -1 to 1. And if you discretize this by finite differences, you come to this kind of equation where A is now this discrete Laplacian in finite differences. And so this is the control system. The cost function is exactly the one that I showed you at the beginning. And then we had the following results. So I would like to recall that we would like to beat the engineering ansatz of using this Riccati solution. So they would just linearize the system, calculate this matrix that is associated to the Riccati, and then use this for the optimal control. And the holy grail is to be just better than this. So the moment you beat the linear quadratic regulator, your method is working. And it turns out that this is very dependent on the initial datum that you choose to evaluate the your optimal control. So we have here two different initial values. So the blue curve is one initial value, and the orange curve is one initial value. And then we evaluated the linear quadratic regulator that is here in blue, and our methods with two different regularization terms that is orange and green. So for the one initial value, that is the one in blue here, you can see that we could improve, but only slightly. And this is not of interest in the optimal control theory. But for the other initial value, we got quite a nice improvement. And so this is, we used polynomials up to degree 7 with a rank of around 8 or 10. So this is very moderate-sized approximation. And this is in 32 dimensions. And in the other plot, we just looked at how good we approximated the value function. You could see that we beat this linear quadratic regulator again. But I think the overall message is that we can improve. Another set of, and then we got interested in what TTs can actually do. And then we started like a small set of examples where we want to test them in comparison to neural networks and kernel methods. And the first thing that interested us was the influence of how regular the function needs to be approximated. So, the square of the norm is a very nice polynomial, and you can approximate it you can approximate it perfectly with tensor trains up to machine precision. If you just take the norm, it gets more intricate already because you have this non-differentiability in 0. And if you take the square root of the norm, it gets even more difficult because also the gradient is suddenly got as infinite in the 0.
So just you have a shift 1, 2, 3, and then 0, 1, 2.
This is just this. Yeah, sorry.
Yeah, just checking.
Yeah, you're right. Yeah. And what surprised us a lot is how good the tensor trains still worked. So I need to say here that we used now TT cross to solve this approximation, this least squares problem, which works somehow very good in this setting. So this is really outperforming the other methods we used for TTs. And it works really surprisingly well. So 10 to the minus 6 is something you're very happy with an approximation of functions. And if you compare it to the neural networks, and the kernel methods, you can see that we outperform them quite a lot. And especially in the neural network setting, they were really big. The numbers of degrees of freedom were really much bigger than in the tensor case. And we trained them quite a lot, so it was in some sense fair because we gave them enough space to approximate. But again, optimizing these neural networks is a very delicate thing. So if this is the best you can really do, I would not say. So it might get better if you put a different architecture or if you train differently or whatever. But if you are not really experienced neural network trainer, then this is probably what you would get if you use it just straight from some library. And here you can also observe very nicely that the kernels generalize really badly. So on the training set, they minimize the loss almost perfectly, and outside the training set, they're not working nice anymore. And we visualized this function. So this was in 16 dimensions, and then you cut out one plane to visualize the function, and you can see that so here is the real function. This is the norm just. And you can see that the TT actually finds it quite nicely. So exact of the point, you can see the shape, and the NN and the kernel surrogate do a very bad job here. But again, you can train it maybe better. And what you also need to keep in mind here maybe is the way that you measure the error. We measure that in some kind of L2 norm. And L2 norms cannot quite see the localized non-differentiabilities where we don't work well. The mass of the area where we are not very well approximating is very small. So it's not seen in the L2 error. So this is one reason why our method, or why TT works so good, because the non-differentiable parts, they are so small that you cannot see them in the L2 approximation. This is something you need to keep in mind if you evaluate the results of the numerics. And lastly, I want to show one more academic control example, because we prescribed the value function. This was to test some other optimal control methods that we used. And here we plotted the approximation error with respect to the dimensions of the test model. So we started with dimension 3 and went up to 16. So this is the dimension of this X. And you can see very surprisingly that the TTs actually get better with the increasing dimension. So this is what is in machine learning sometimes, also observed that high dimensions maybe actually help, but nobody knows why exactly. However, the kernel methods and the neural networks, they get quite bad. So an error of, 30% or something like this is not acceptable in scientific computing at all. But again, this might be due to the training of the neural network, that it's not quite that what you want.
Yeah, it'd be more fair if you had your group getting together with the neural network group, getting together with kernel group, and all three of you
it was
the same challenge problem to
So
work on, rather than
the kernel was done by an expert in kernels.
Okay.
And he also, since years, always uses neural networks to compare his methods to the kernels. So it was somebody who has experience with neural networks. The question is how much, to find a nice architecture in neural networks might be a matter of half a year or more. So it depends really on how much effort you want to put. But this is why I'm always saying that the neural network numbers should be taken with care. The kernel methods are what our expert did. So this is really the best you can do. All right. And so I think that overall, in the context of optimal control at least, you can use all three methods actually quite nicely, but TTs is really good. I mean, they work nice for really various examples, because there are other groups in Europe that also uses this TT in the optimal control setting, and they got similar results as us. And we think that there is some kind of structure in the problems that we looked at that somehow are very beneficial for TTs. And in our opinion, it is this kind of locality in the dynamical system, so that you have a very small interaction and always between nearest neighbors. This somehow seems to be reflected in the performance of the TT. And this is something we really would like to prove, and where I would really like to get some input from probably the physics community, who would have a lot of this intuition about how locality reflects in the bond dimension. But so this is one of the open questions we really would like to answer next, is on why the TTs are so good in this optimal control setting. And with this, I would like to thank you.
Thank you.